Let's see an example of the EM algorithm of the normal mixture motivating example we mentioned earlier. We consider the familiar two-component mixture model of two Gaussian distributions. We know that for this distribution, the mixture distribution, the corresponding PDF is given by this form over here, where we have the weighted sum of two normal densities. In this case, F1 and F2 denote the normal PDF for two normal distributions with means of mu1 and mu2 respectively, and variances of sigma squared 1 and sigma squared 2 respectively. For this particular model, the data we usually observe are the x's, right? The observations that are drawn from this distribution. The unknown parameters in this case to be estimated include the mixing proportion p, which tells us what is the chance that someone stems from the first normal distribution. As long as we know that, we know for the second normal distribution, the chance is 1 minus p. And the other parameters include the means and variances of the two normal distributions, mu1, mu2, sigma 1 squared, and sigma 2 squared. Given this case, we know that the observed data likelihood is given by the product over all of the samples, the sample size equals small n, of this weighted sum of the two normal densities. But you can see that this function is actually very tricky to deal with analytically. If you take the log of it, it's going to involve the log of a weighted sum of two densities, which is difficult for you to further break down. However, we saw that we can use the, if we work instead with the complete data likelihood, which includes not only the observed x's, but also the latent group memberships, yi's. In this case, the complete data likelihood is given by the joint probability or joint distribution of y, the group membership, and the x's, conditional on the group membership across the observations given theta. In this case, the likelihood is given by the product over all n samples, the probability that someone stems from his or her particular class, so the yi class, times the corresponding normal PDF for that particular class. You can see that this thing is, if you take the logarithm of it, it's going to have a much simpler form. Right? It's going to take this form on the last line, where you can see that you can even further break it down to the sum over all n samples, the log of pyi minus log of square root of 2 pi sigma yi minus this part that was on the normal density exponent. Okay, so let's see how the EM algorithm can be used in this case to estimate our 5 parameters, which includes the p, as well as the mu and sigma for the two normal distributions. Recall that in the E step, we want to compute the Q function, right? Which is Q of theta given theta old, where theta old is in general the parameter estimates from the last iteration. By definition, we need to first find out what is the conditional distribution of the missing data y. In this case, the missing group memberships, given the observed data x and the thetas, which are the p, mu, sigmas from the last iteration. And then under that conditional distribution of the group memberships, we find out what is the complete data likelihood given by L of theta of both x and y. So in our case, this is given by the following form over here, which is essentially the sum over all n's of this complete data likelihood times the probability that the yi is equal to a particular j, given the xi and the thetas from the last iteration. So what is this later term over here? So you can see that we're essentially summing over the two possible classes, the complete data likelihood, and plugging in that particular j, and the probability that yi takes that particular j, which is either class 1 or class 2. So this later term is essentially given the observed data xi, as well as the theta estimates, the p and the mu and sigma from the last iteration. What is the conditional probability that yi, the class membership for the ith observation, is equal to j, where j is either 1 or 2, right? We know that this will be given by the joint divided by the marginal, or you can see that the numerator over here is essentially the probability, population membership probability from the last iteration, pj old. So it's either p from the last iteration or 1 minus p, depending on whether your j is 1 or 2. Plus the normal PDF of the j class, j is 1 or 2, given the mean and variance estimate from the last iteration. And the denominator is essentially the sum over each possible class, right? In this case, j of either 1 or 2 of the p old times the corresponding normal density. One thing I want to point out over here is that you can see in the Q function, there are some terms over here like pj and sigma j and mu j, right? These terms that I noted in blue are not the old values from the last iteration. The old values from the last iteration actually comes in the p theta old part, where we have to use the mu and sigma squared from the last iteration to see what is the conditional probability given this observation's x, that this this sample's y is either 1 or 2. That's the part that the theta old comes in. But the parameters noted in blue over here, they are not the old values. They are the variables or the thetas that will influence the size of the Q function. And these are the things that we are going to try to find the optimum for if we want to make Q as large as possible in the M step. So in the M step, essentially we search for the P and the mu J's and sigma squared J's so that our Q theta given theta old is as large as possible. What you can do is very similar to before. To find the optimum, what you can do is to take the first derivative and solve for its root, right? So that's what we can do over here. We can take the partial derivative of the Q on the last page, which involves these variables, with respect to each of the parameters that we are interested in updating. If we take the derivative with respect to P and set that first derivative to be equal to 0, what you'll find out is that the Pj nu, which is the optimal P that makes Q prime with respect to P equal to 0, is going to be given by 1 over n times the sum of the P theta olds across the I observations for class J. For J of either 1 or 2, the new normal mean estimate is going to be given by this fraction over here, where the numerator is going to be the sum over all n samples, the xi, the observed xi, times that P theta old, that observation I stems from class J, given the xi and the old thetas. And the denominator is going to be the sum of the n P theta olds, which are the conditional probabilities that each observation comes from class J. So taking the ratio over here gives you the new mean for class J in that iteration. The sigmas, you can see it has a similar idea. Essentially, it's going to be a function of the P theta olds as well as the sum of the squared deviation of each of the observed xi's and the mu j we just got from the last step. One thing I want to note is that here we're dealing with two classes, like a mixture of two distributions. And in this case, P2 is actually equal to 1 minus P1. However, the formulas above are also generalizable to more than two classes. So in those situations, the formulas you have here are still applicable, as long as you're dealing with normal mixtures of, say, 3 or 4 normal distributions. All right, so from now on, let's see how to implement that inside R. We're going to conduct a simulation study where we start from generating some data from the mixture of two normals, where we know what is the ground truth P. In this case, is equal to 0.2, and we know what are the ground truth mu's and sigmas for the two distributions. As you can see here, we're setting the two variances to be both equal to 1 and the two means to be 3 and 5, respectively. Each observation has about 20% chance of coming from the first normal distribution with mean 3. And let's use a sample size of 5,000 in this case. The code below essentially performs what we learned in week 2, which is given some true parameters, how do you generate data, the x's from the mixture distribution. Again, similar to before, we first generate the group memberships, which we call I over here. It's the sample from 1 to 2 of size n. So for each sample, we sample from 1 to 2 the group membership, either 1 or 2, where the probabilities of the two groups is given by 0.2 and 0.8, respectively. Given the group membership, we generate the corresponding x, which follows a normal distribution, and the mean depends on the group membership. The variance also depends on the group membership. Let's know that this is how we generated data, right? But in reality, we actually will not observe the i's. So we don't know which group each individual comes from. What we instead only observe are the x's, which essentially looks like this. One thing to note here is that maybe from your first homework, you remember for mixture of two distributions, if the mixing proportion is very imbalanced, you might end up with a unimodal distribution. So this will be one of those cases where just looking at the histogram, you can't tell actually there are two modes, right? So this is the data we observe. Let's try to use this data and implement the EM algorithm. In each iteration, we're going to run the E step and the M step. Let's set some initial values first. Let's say our initial value for P is going to be 0.5. So that's our first P out. The means initial values are given by 0 and 1. And the sigmas, let's suppose that our initial values are 3 and 3 for the variances. Let's create a function for computing that's important probability that comes into almost every step of the EM algorithm, which is conditional on the current parameter estimates and the xi, which is the observed x for the ith individual, ith observation. What is the probability that the group membership for sample I is equal to j? Let's recall that this is given by this fraction over here, right? Where if you want the probability stems from group 1, on top you will have the P old times the F1, the first density, where you plug in the xi and use the mu1 and sigma square 1 from the last iteration. The denominator essentially sums over the two possible classes, the thing that comes in on the numerator. So this CY function actually performs this. It takes inputs of x. P is the last iteration's mixing proportion. Mu's and vars are the last iteration's means and standard deviations, so the old guys. To find the numerator, what we can do is essentially having the P times the corresponding normal density for the two classes. So if you do like a vector of the P for class 1 and the P, which is essentially 1 minus P for class 2, times the D norm, the normal density, evaluated at x, but with two possible mu's and two possible standard deviations for the two classes. And that's our numerator. It's going to be a length 2 vector that gets for j equals to 1 and j equals to 2, what is the numerator going to be? You can see that the whole thing for j equals to 1 and j equals to 2 essentially will be given by the numerator divided by the sum of the two entries on the numerator. That's this summation of k from 1 to 2. So that's what this function returns. Essentially, it gives you for the two possible classes, j equals to 1 and j equals to 2, given this xi and the last iterations p and the mu's and sigmas for the two classes, what is the probability that yi is equal to that particular class? This function is going to be called in each iteration when we try to find the current maximum of the two functions. So let's run one iteration of the EM algorithm first. In the E step, we want to get the Q function, right, which is essentially the expectation of the log likelihood given that conditional distribution of y given x and theta old. Essentially, what we need to get in the E step over here is the p theta old for each of the I observations. So what we can do is to do a supply over all of the x's. So that does the vectorized entry-wise operation. Where to each of the entry of x, we're going to apply this function py and say that our p, so the remaining arguments of this function, are going to be the p, the two mu's, and the two variances from the last iteration, right, the old ones. For the first iteration, it's just going to be the initial values. You can see that the result of py's is going to be a 5000 by 2 matrix, where if you look at the first 6 rows, that corresponds to the first 6 samples. Essentially, these two columns sum up always to 1, right? The first column gives you the conditional probability that this particular sample is believed to come from class 1. Second column, of course, gives you the conditional probability that this observation comes from class 2. Okay, so it suffices for us to get that in the E step. In the M step, we know exactly how we can use the p theta o's to get the optimizers to each of the parameters, right? So let's first begin with updating our p's for the two classes, right? Essentially, all we need to do is to get what is the new p for the first class, right? Because we know the second class is going to be given by 1 minus that p. So in this case, we can use the earlier formula we saw, where essentially these are the solutions to root finding for the Q partial with respect to each of these parameters. For P, we know that it's going to be given by the sum, actually the mean of the n p theta o's. Right? Essentially, so what we had on the last page, you take the first column, which gives you for each of the 5000 samples, what is the conditional probability that it comes from class 1? You take the average of that, and that gives you the new estimate to P1, which is the overall chance that a observation comes from class 1. In this case, let's say we're going to update the value of P0 to this new mean of the first column. And for this particular iteration, we have updated it to be equal to 0.21. Now we can try to find the updated values of mu1 and mu2 by applying the earlier formula. Let's recall that we will need to get the numerator and the denominator, where the numerator is going to be the sum over all n, the xi's, times each observation's corresponding p theta o's, and yi comes from class j. The denominator is also a sum that doesn't involve the xi's. So we can first get the numerator that's given by the py's we had earlier. So if you take this matrix and multiply both columns by x, essentially you get a new matrix, right? And if you take the column sum, essentially it does the sum over all n's of the xi's times the p's, where you end up with 2 entries, one entry for the numerator when j is equal to 1, and the other entry is for when j is equal to 2. And then your mu updated values is going to be that 2 sums divided by simply the column sums of this py's matrix. Right? It's essentially for both classes, the sum over all n, the probability that someone comes from that class. Right? So that's our updated mu old. And in this case, in one iteration of EM, we have updated these two values to be having means of 4.15 and 4.71 respectively. Last thing we need to update are the variances of the two normals. It's given by this formula here that you can see still involves p theta old, as well as the square deviation of each observation from the mean of that particular class we got on the last page. So what we can do is first, again, get the numerator. In this case, we will need to know across the n observations, what is the square deviation of each observation from the two means we got from the mu modes. So that's called square depth. If we multiply this thing by the P matrix, the P-wise matrix that we saw earlier, take the column sums, that gives you the numerator. The denominator is again the column sums of the P-wise matrix. And we can see that in one iteration of EM, our updated sigma square O's are going to be 1.78 and 1.55 respectively. Okay, so that's one EM cycle. We did one E step where we updated that conditional probability that each observation comes from each particular class. And then we use that conditional probability to figure out which should be our new parameter estimates for the P's, me's, and sigmas. For the EM algorithm, you will need to iterate it for a large number of times. So how about we try to do it for 1,000 iterations? Let's create a matrix called beta, which has a total of 1,000 rows and 5 columns. The 5 columns are going to be used to store the P, the 2 mu's, and the 2 sigmas. And then in each replication R, in each iteration R, we repeat what we just did in one EM cycle. We first do the E step, where we update the P-wise, plugging in the current values of P old, mu old, sigma square old. And then in the M step, we use the P-wise we just got from the E step to update our P old, mu old, and sigma square old. We're going to store these P old, mu old, and sigma square old in the rth iteration into this beta matrix, so we can keep track of how it changes over the 1,000 iterations. Okay, so after 1,000 iterations, we will get a last iteration's P old. Right? In this case, it's given by about 0.29. And the mu and sigma square olds in this case are given by these numbers over here in the 1,000th iteration. What you can see is that actually all of them seem a little bit off from the true value we used to generate the data. However, it does seem to improve over time. So what's happening over here? Did it not converge? Actually, that's not the case. If we actually look at how the thetas, so each of the 5 possible parameter changes across the iterations, you can see that all of them seem to have converged and stabilized. Just looking at the graph, it seems like for example, the mu2 stabilized at somewhere that's close enough to the true value of 5. And for mu1 is stabilized at somewhere that's close enough to 3, but slightly off. But why are they all slightly off? Well, there are 2 possibilities. The first is that when you have a finite sample, the actual mean or standard deviation and mixing proportion are going to deviate slightly from the theoretical values that you use to generate the data. However, another thing is that because we have a case where we have 2 mixtures that are kind of so close to each other, the algorithm is going to have some hard time differentiating whether each observation comes from the first latent class or the second. And that actually makes accurate estimation harder. But that's the idea of the EM algorithm applied to the estimation of parameters for the normal mixture. What we can also check in the EM algorithm is whether the observed log likelihood does seem to be increasing in each EM iteration. So let's recall that the observed log likelihood is going to be the sum over all of the observations, the weighted version of the densities. Right? So in each iteration, what you can do is to take the current P old, the current mu old, sigma olds, and then compute the weighted density, right, which is given by log of F1 plus F2. So you can see that here is F1 plus S2. It doesn't have the weights because we already multiply it by the current P when we get F1 and F2. Okay, so this function over here takes the theta matrix and your observed x's, and it returns for you for each iteration what was the observed data log likelihood. Let's note that this is never the thing we directly try to optimize, but does it actually try to improve, seem to improve over time? Okay, if we plot over the 1,000 iterations, all the log likelihood, plugging in each iteration's thetas and the observed data changes, we can actually see that it does seem to improve over time. Right? At some point, it seems to be not improving anymore. So that might be the point where it actually converged, and running further iterations doesn't seem to improve the results.